Welcome back, folks, and glad that you tuned in. So now we move to the algorithm called OCLUS, which stands for Arbitrarily Oriented Projected Cluster Generation. It is claimed to be the first approach to generalized projected clustering. However, as we know now better, it is not really the first one, because local PCA from 1993 already did that trick. It is a generalized projected clusters. It is stated here, like to obtain generalized projected clusters is a set of vectors E, actually the eigenvectors or principal components, and a set of points or objects C, such that the points in this cluster C are closely clustered in the subspace defined by the eigenvectors E. So E is a set of orthonormal vectors, just like from a PCA. So if you got this one here as the first and this as the second, these two are orthogonal, meaning that this one principal component, first principal component, is orthogonal to that second principal component. And what holds is that the cardinality, so the number of these eigenvectors, is less or equals the dimensionality of the original features, dimensionality of the original data set. So if you've got a three-dimensional data set, like here we are in space, three-dimensional, then the number of eigenvectors can be at maximum 3, but they can also be 2 or only 1. And the input of this algorithm is, like local PCA, the number of clusters K. Okay, so with this you mediate the number of partitions, and the dimensionality of the subspaces of the cluster L, where L corresponds to the number of eigenvectors E that you're choosing. However, one word of caution. In local PCA, we said that the subspaces that we have there, like if it's an m-dimensional subspace, it is the one subspace with the highest variance, the correlation subspace. While here, the meaning is the cluster subspace. So if you've got E equals 2, then it means that it's looking for these two subspaces that have the lowest variance. Because remember, if we project these objects down to these two principal components here, to these two that we have, then they will be maximally compact and therefore a dense cluster. So here the notion of L for the subspace dimensionality pardon, refers to the L subspaces with the L lowest corresponding eigenvalues. And what we obtain is a set of K clusters and their associated subspaces of dimensionality L. So to find the subspaces of a cluster, Ci, we compute the d times d, so number of dimensions that we have, d times d covariance matrix, Mi. As you recall from PCA, the covariance matrix has the dimensionality d times d, where d denotes the number of features, dimensions that we have for a cluster Ci, and we determine the eigenvectors. So as soon as we have a covariance matrix, you know, from PCA, we can perform an eigendecomposition, solving the eigenproblem, and obtain eigenvectors and their corresponding eigenvalues. And from these eigenvectors that we have here, we pick the LC eigenvectors with the smallest eigenvalues. So we pick for that particular cluster C, those L eigenvectors that have the smallest. So if we have, like here in this example, 3, 1, 2, and 3, we pick those, for instance, L equals 2, we pick those two here with the smallest eigenvalue, and we discard that one, because projecting the objects from this one here down to these two will yield a compact, dense cluster. It relies on a cluster-based locality assumption, meaning that the subspace is actually learned from its cluster members that we have here. The idea behind OCLUS is similar to ProClus, by the same authors, by the way. While ProClus is an axis-parallel subspace clustering, OCLUS is the generalized, arbitrarily oriented version. And at this point, yes, indeed. So with arbitrary oriented subspace clustering can be regarded as a generalized version of the axis parallel subspace clustering, where it's limited to the axis, and with correlation clustering, we are no longer limited and can also have axis parallel if available, but we can detect any arbitrarily oriented subspace cluster. It has a k-means-like approach similar to local PCA. The interesting point is we start in the beginning with KC initial seeds, where KC is larger than the expected K. Now you may say, why, why are we, or how, and when, and why? The idea is that we have in the beginning more seeds than actually expected, or there's actually by the user parameter K defined, and these Ks are then merged with each over the iterations. So it works as follows. It assigns a point to a cluster according to a distance function, which is based on the eigensystems of the, eigensystem in the sense of eigenvectors of the current cluster. And in the beginning, it starts with the axis of the entire data space. So let's say in the first iteration, it just computes the Euclidean distance. It performs like the first step of a k-means clustering. Take all the dimensions that you have. However, then the eigensystem is iteratively adapted based on the updated cluster members. So after the first step, which is over all dimensions, we have an assignment, and then it starts to compute the eigensystem, the subspace that we have, and it continues to update it over the iterations. And however, we still have this problem, like we have more clusters initially than we actually need. Here, we reduce the number of clusters KC in each iteration by merging the best fitting cluster pairs. So let's say we have one cluster like this and another like this, and we want to say, okay, those two, they have like this similar orientation, so let's merge them together to one cluster. But this raises actually up the question, what is the best fitting cluster? How do we determine it and get our head around that issue? So for this, consider each cluster Ci exists in a possible different subspace Si. How do we make this decision, merge or do not merge? For this purpose, we compute the subspace of the union. So let's say we have here this subspace eigensystem 1, and we have here this eigensystem 2. Subspace 1, subspace 2, subspace 1 here. We compute the union, so the union of both, now in green, would be this here. So these two arrows, this eigensystem, these spanning eigenvectors are emerged, or have emerged from the union of the eigenvectors from cluster 2 and cluster 1. Then we check the so-called cluster energy of Ci and Cj, or union with Cj in this subspace. This is one of the fancy terms which, to my personal opinion, is a personal opinion, nothing more, is used way too often in different contexts. Something like energy, you know, mostly from the context of physics or chemistry probably, but not in computer science necessarily. So what is meant here with cluster energy is you take all of these green objects and you press them down, you project them down to this cluster subspace, to this one here, which has the lowest variance. And then when projecting them down to this axis here, we compute the mean square distance of the objects to the centroid. So we project all of these green objects to this small arrow here. And then we compute like we first compute the mean, the centroid, and then we compute the deviation of all the objects to the centroid. And by this, so by having, so to speak, the variance, and this is basically cluster energy, you can consider the cluster energy as the variance of objects in the cluster subspace from the union of both subspaces. And this is the term of variance, cluster energy is equal to variance of objects to their centroid in the union of the subspaces here. And this is considered as an indicator of how good the points of two different clusters combine and if they should be merged or not. Excuse me. So it assesses the average distance in all merged pairs of clusters. So this is like these two clusters, if there would be a third cluster, then this one would be with the next one. So you have all the possible pairs of clusters, it merges them, and then it takes the one pair of clusters, like in this case, these two, because they kind of suit really well. Then they are being merged or considered as to be merged clusters, and therefore also merged subspaces. And this approach is continued until we obtain the number of clusters k that we originally handed over as a parameter. So these two, suppose there's also a third one here, which would be like this, and say this third one with this here does not fit well. The projected energy would be way too high. This here with this one would be too high, but these two here have a low projected energy, a low variance in cluster subspace, and therefore these two are merged. So that about Oculus. You see, in a nutshell, we are not going into the specialties. There are also some tuning parameters, alpha and beta, and some extensions and whatnot, and how the algorithm works, all the lines of the code. No, these are things you can look up, but what you should, or what is not necessarily something that you look up, but that you can absorb and capture now, are these core properties, or how roughly it works. Regarding the core properties, it performs clustering in a k-means fashion. It is controlled by two parameters, number of clusters, k, and the subspace dimensionality, L, which denotes the dimensions from the eigensystem which have the L lowest variance. Excuse me. And something that is interesting, we shall see that not all algorithms have this advantage or disadvantage, depends, is that this parameter L holds for all clusters. So you cannot say that cluster should be two-dimensional, that one should be one-dimensional, this one can be three-dimensional. If you set this L, it holds for all clusters. So if L equals 2, then all detected clusters are going to have the dimensionality of 2. And one issue, similar to local PCA, it does not have native outlier handling. So you can or could extend it, and there is also proposed in a paper how to introduce outlier handling. However, in its native form, it does not have it. This is problematic since, as we had it in local PCA, outliers can potentially distort the orientation, the variance of the eigensystems, and also the translation. And one aspect which may seem kind of minor, but it's interesting to investigate. So this is also a potential bachelor master thesis or project we can sit together. In its native form, this algorithm is highly susceptible to an ill initialization of the random seeds. If you know, for instance, the classic k-means algorithm, it is also exposed to this ill initialization. If you're unlucky and choose unlucky initial centroids, it may happen that you obtain clusters which are really weird, and you say, no, the cluster should look like somehow other, because there are two random seeds, two centroids randomly initialized that are like tearing a cluster apart into two clusters. For the classic k-means, there is a remedy to it known as k-means plus, and here I owe you the reference that I see, because credit where credit is due. And k-means plus is a method which mitigates this effect of ill initializations. However, Oculus does not have it, and as far as I've looked it up so far, maybe you have better luck and say, oh, but I found that paper, that would be great. As far as I've looked, there is not a method which proposes a remedy to this ill initialization. So if you're interested and say, hold on a second, I think I can incorporate something like k-means plus into Oculus and providing this remedy, making it robust against ill initialization, write me please an email, hit me on that, let's have a Zoom meeting. This is like an interesting or exciting aspect to do research on. It may seem small, so you say, okay, so what? I'm improving the initialization. Nevertheless, solving this may, on the average, yield to better results being more robust. And well, this is it so far about Oculus. And stay tuned for the next correlation clustering algorithm. In this sense, see you later.